The most powerful weapon in the AI arms race isn't a model, it isn't a data center, it isn't even a chip. It's a $380 million machine. That one Dutch company has a total monopoly on building, and right now, the US government is using it as a weapon. China is desperately trying to work around it, and most people have never even heard of it. This is ASML's EUV lithography system, and there is exactly one company on the planet that can build it. Every AI accelerator currently running the models you use, every single one, physically passed through a machine like this before it reached you. No ASML, no chips, no AI. That's not a metaphor, that's physics. Here is the problem at the heart of everything. To build a modern AI chip, the kind running GPT-4, the kind inside Nvidia's Blackwell accelerators, you have to etch features onto silicon at scales almost too small to imagine. We're talking transistors measured in single-digit nanometers. For context, a strand of human DNA is about 2 nanometers wide. These chips are being carved at that scale, but you cannot use normal light to draw something that small. Visible light runs between 400 and 700 nanometers. Even the most advanced deep ultraviolet lasers sit at 193 nanometers. You are trying to paint a masterpiece with a brush that's literally 100 times wider than your canvas. So, you need light at 13.5 nanometers, extreme ultraviolet. Light so short wavelength, so energetically aggressive, that it doesn't naturally occur anywhere on Earth. It gets absorbed by glass, by air, by water, by almost everything. So ASML and its American subsidiary Cymer had to manufacture it from scratch. Here's how. A nozzle fires a droplet of molten tin into a perfect vacuum. The droplet is 30 microns wide, smaller than a human hair. It falls. A laser snipes it, not to destroy it, not yet. This first pulse flattens it, turns a falling bead of liquid metal into a microscopic tin pancake, suspended in the void. And then, microseconds later, a second pulse hits it with everything it has. The tin doesn't just vaporize, it annihilates. The plasma burns at roughly 220,000 degrees Celsius. That is approximately 40 times hotter than the surface of the sun. And from that screaming, star-hot cloud of obliterated metal, EUV light is finally born. The system fires this entire sequence: tin drop, first pulse, second pulse, plasma, light, 50,000 times per second, every second, all day, without a single miss. A physics sniper, operating at the speed of manufacturing. That is not engineering in any conventional sense. That is violence dressed up as precision, and it is only the first act. Everything you just watched, the atomic precision, the billions in R&D, exists for one purpose: making compute cheaper. That same curve is quietly making manual coding replaceable, not someday, already. Most engineers won't notice until it shows up in a layoff memo instead of a headline. I wrote the 2026 displacement report to close that gap, what's actually happening, and the 3 specific skills that determine who's still employable on the other side of this. It's free, it's 3 pages, and it's the one thing on this channel I'd actually tell a friend to stop and read. Links in the description and pinned comment. Grab it before you close this tab. It's easy to mean to and never do. But hardware is only half the battle. Now let's look at the impossible mirrors inside the High-NA EUV systems. You might think, okay, we have the light. The hard part is over. It is not over. EUV light is so aggressive that it refuses to pass through anything. Glass, absorbed. Air, absorbed. A conventional lens, absorbed immediately. The entire paradigm of optical engineering, a paradigm that has guided photography, telescopes, and microscopes for 4 centuries, simply doesn't work here. So Zeiss had to abandon lenses entirely and rethink the concept of optics from first principles. The answer was mirrors, but not normal mirrors. These are Bragg reflectors, built from up to 100 alternating layers of silicon and molybdenum. Each layer just a few atoms thick, stacked with sub-nanometer precision. The EUV light bounces off these layers the same way sonar bounces off the ocean floor. Each layer reflects a tiny fraction, and together, they build up a usable beam. But here's the constraint that makes grown engineers lose sleep. Any surface defect, any bump, any atomic scale imperfection will scatter the EUV beam and corrupt every chip the machine ever touches. So, Zeiss had to build the flattest surfaces in the known universe, 1 red blood cell tall. If you took one of these mirrors and expanded it, in your imagination, to the size of the continental United States, every mountain range, every canyon, across the entire country, would rise no higher than a single red blood cell. Zeiss polishes these mirrors 1 atom at a time, using ion beams, then verifies the result with interferometers sensitive enough to detect deformations smaller than the nucleus of a single atom. 6 mirrors, each one, by any normal standard of engineering, impossible. all 6 operating in perfect concert to steer a beam of plasma light, 13.5 nanometers wide, onto a piece of silicon the size of your palm, and they have to do it without drifting, without thermal expansion warping the geometry, without a single photon landing a nanometer off its mark. But EUV light is absorbed even by trace molecules in a near vacuum, so the entire interior of the machine has to be held at 1/billionth of atmospheric pressure, a vacuum so deep it makes the lunar surface look crowded. This means everything inside, every moving part, every mechanical component, has to operate under conditions that make space-grade engineering look casual. That's where VDL-ETG enters. VDL builds the wafer stages, the robotic platforms that hold the silicon and move it beneath the beam. But here's the problem. In a vacuum this deep, you can't use ball bearings. They'd release gas and contaminate the mirrors. You can't use lubricants. They'd vaporize. Any friction-based mechanical system fails. So VDL levitates them. Electromagnetic tracks lift the wafer stages completely off the surface. They float. They're driven by linear motors, the same technology that powers maglev trains, miniaturized to fit inside a machine the size of a delivery truck. And then they accelerate. Hard. These stages pull multiple Gs, more G-force than an astronaut during a rocket launch. The silicon wafer, a disk of ultra-pure crystal worth thousands of dollars, is hurled back and forth beneath the beam at speeds that would register on a speed camera. But speed, here, is not the point. The point is where it stops. 1 nanometer accuracy. After every pass, after all that acceleration, all those Gs, the stage decelerates and repositions to within 1 nanometer. That is smaller than most proteins. Smaller than the width of your DNA strand. Imagine a commercial airliner at full speed pressing its brakes and having its nose gear land on a single human hair. So precisely, it doesn't even graze the adjacent strand. Now do that millions of times a day, without ever drifting, without ever flinching. 3 systems, 1 machine. Cymer births a star. Zeiss captures its light. VDL moves the canvas with nanometer precision. And they do it all simultaneously, in perfect sync, inside a warehouse in the Netherlands. This convergence doesn't come cheap. ASML's standard EUV system, the low-NA generation, already costs between $183 million and $235 million per unit. But the latest generation, the High-NA EUV, the Twinscan EXE5000 and EXE5200, takes the price to a different stratosphere entirely, $380 million per machine, and requires up to 2 megawatts of continuous electricity, enough to power a small town, just to turn one on, before the $20 to $25 million annual service contract, depreciated over 7 years. That is the price of admission to the next era of computing, and the semiconductor industry is at war over whether it's worth it. Intel is going all in. Their upcoming 14A node, slated for risk production around 2028, is built around High-NA EUV. The logic is clear. A single high-N A exposure can print features that otherwise require multiple complex, multi-patterning steps with older tools. Intel calculates this translates to 15 to 20% better performance per watt and up to 35% lower power consumption compared to their current 18A node. For a company fighting to reclaim process leadership, the $380 million price tag is, in Intel's own words, the necessary price of admission. Intel CFO David Zinsner confirmed it plainly. The 14A node will be inherently more expensive to produce than 18A, directly because of these machines. But TSMC, the world's dominant pure-play foundry, running operating margins of nearly 58% as of Q1 2026, is refusing to blink. Their position? The $380 million machine is a margin killer for current generations, and their mastery of existing multi-patterning techniques using older low-NA tools is simply more cost-effective right now. Their upcoming A13 and A12 nodes will not use high-N. They plan to hold until they reach 1 nanometer class architectures, where multi-patterning becomes physically impossible. Kevin Zhang, TSMC's deputy co-CEO, put it this way: "This is where I think our R&D has done exceptionally well in terms of leveraging existing EUV technology while setting an aggressive technology scaling roadmap. 2 of the most sophisticated technology companies on Earth, looking at the same machine, reaching opposite conclusions about whether to buy it. That tension alone tells you something important about the stakes of what ASML has built." Thanks for watching this video. If you want more breakdowns like this, hit the subscribe button and turn on the notification bell so you don't miss the next one. See you in the next one.